The scenario considered in this demo targets a specific use case where a software vendor develops, trains, and deploys an ML-based model for a mobile network operator. The software vendor and MNO domains have been instantiated on different VMs to simulate the separation between these environments. The software vendor workflow targets the AI model development, including getting anonymized training data from the MNO, model design, data validation and preparation, model training and testing, local model storage and propagation of the model towards the MNO. The MNO validation workflow occurs in its staging environment, including verification of the model delivered by the vendor, acceptance and deployment in the production environment. The MNO deployment and operation workflow occurs in its production environment, including deploying the model in production, continuous monitoring of model performance and drift detection, as well as triggering model updates. The demo begins with a clean staging environment, with no models deployed or running in the MNO environment. The API exposure service in the MNO staging environment returns an empty response body, signifying there are no serving models. The model storage of the MNO, stored in an instance of min.io, does not contain any saved models. The TensorFlow serving configuration file, also stored in the instance of min.io, contains no model information, signifying that there are no models loaded in the software package. This is also verified through the TensorFlow serving API. There are no model monitoring topics in RabbitMQ, which are used by the model monitoring to alert the orchestrator of deficiencies in the model forecasts. The MNO staging environment is receiving runtime data from the production environment, which will be used to test the accuracy of trained models sent by the software vendor. The software vendor workflow begins when the staging environment sends anonymized training data. The anonymization process implemented for this scenario is based on the so-called microaggregation method. The objective is not to share with the software vendor the actual measured data, which are considered confidential, but some other equivalent data derived from the measured data that can be used to train the machine learning model. In this case, as an example, the anonymization process is applied to the packets received and the packets sent parameters, which are numerical values. The process basically consists in clustering and averaging the original data to produce new data in the same range of values. In this slide, we can see how this clustering and averaging process is performed. The original values are sorted to group together those with a similar value. Then the average of each cluster of values is computed. What is transmitted to the software vendor are the averages, hiding in such way the original values. Of course, this anonymization method is very specific, and only works for numerical values. For other data types, other anonymization methods can be considered. Here we can see the anonymization process running. Original data are stored in the 6-week sim CSV file. After executing the anonymization process, encoded in the mant.jar file, the new values are stored in the new generated CSV file with a timestamp. This is the file that is sent to the exposed dataset database to be consumed by the vendor. The sent data can be seen in the software vendor local storage. The software vendor uses the data to tune and train a model for the MNO. The training pipeline for UPF traffic prediction using ML is executed in kubeflow, specifying the name, version, data endpoints and a defined target accuracy. kubeflow executes the pipeline, deploying each training step in a separate Kubernetes pod. The Kubernetes UI allows inspection of the results of each training step, including training performance and KPIs. The model is stored both locally at the software vendor as well as propagated to the MNO, if the trained model KPIs are in range. The trained model and attributes can now be seen in the local storage of the software vendor, organized by model name and version. The trained model is then propagated to the MNO via an API exposure service. The staging environment exposure service receives the model from the software vendor, which triggers the MNO validation workflow coordinated by the staging orchestrator. The MNO model storage now contains the model and associated attributes, ready for evaluation. At this point, the staging environment exposure service notifies the orchestrator about the availability of the new model, and the validation workflow can start. The TensorFlow serving configuration, which contains models and versions to be loaded by TensorFlow serving, is updated by the staging orchestrator, and now contains the information on the model sent by the software vendor. When queried, TensorFlow serving now shows that the new model has been loaded and is ready to be used and evaluated. The AI agent and the model monitoring are configured to use the new model and version, and are started by the staging orchestrator. This can be seen by querying the AI agent's current configuration. A dedicated topic is created in RabbitMQ for the model monitoring to publish potential model drifts. The staging environment DB is now receiving model predictions from the AI agent and efficiency readings from the model monitoring, as can be seen on the Grafana dashboard. During the evaluation period, any model efficiency issues are posted by the model monitoring on RabbitMQ. If no messages are posted by the model monitoring after the evaluation period, the model is ready for deployment in production. After the evaluation period, the model is ready for production. The staging AI agent and model monitoring are stopped by the staging orchestrator. The model is then propagated to the production environment via the production API exposure service, which triggers the deployment of the model in production. The production API exposure service can be queried to retrieve the new available model. At this point, the production environment exposure service notifies the orchestrator about the availability of the new model, and the deployment workflow can start. The production model storage, an instance of min.io, now contains the model and associated attributes to be used at runtime for forecasting future UPF behavior. The TensorFlow serving configuration, which contains models and versions to be loaded by the production TensorFlow serving, is updated by the production orchestrator, and now contains the information on the model sent from staging. When queried, TensorFlow serving now shows that the new model has been loaded and is ready to be used in production. The production AI agent and model monitoring are configured to use the new model and version, and are started by the production orchestrator. This can be seen by querying the AI agent's current configuration. The model is now deployed and used in production. The results of the AI agent predictions and model monitoring evaluation can be seen on the Grafana dashboard. In particular, the model accuracy is continuously monitored to detect model drifts. In the case of a model drift, the long-term accuracy of the forecasted metrics falls below tolerance. The model monitoring uses an evaluation time window and a threshold, provided by the orchestrator, to determine that a model drift has occurred. When a drift is detected, the model monitoring triggers the drift workflow by publishing a message on RabbitMQ containing information on the model and version, performance degradation, expected performance, and time period when the drift was detected. The production orchestrator stops the AI agent and model monitoring and checks the model storage to see if a new version of the model indicated in the drift message is available. If a newer version is available, the orchestrator updates the AI agent and model monitoring to use the new version. The production environment then returns to the operation workflow, using the new version of the model to predict optimal UPF scaling operations. The accuracy of the new version of the model continues to be monitored to detect future model drift.